So here are a few animations that will go along with the information that we just learned in the first two lectures. And so hopefully these kind of help show you from a functional standpoint what a system or a schematic that you're drawing is going to look like. So here's the definitions. Again, we know what the system is. It's whatever we are going to study, what we are looking at. And everything external to this system is the surroundings. And then that is separated by a boundary that can be real or imaginary. And then again, we have two basic types of systems, and they are closed systems and then control volume. So let's look first at a closed system. So here's a closed system. You see we have some moving boundary work being done up there by the piston. We also have some heat transfer coming in through the left. We've got some shaft work going on, spinning, and some electrical work. Of course, this is just to show you the different types of work and energy transfer that can be done. And you have the surroundings, and you see here that we have a boundary into it, right? So this is a closed system. It's defined when a particular quantity of matter is under study. And in a closed system, no transfer of mass across the system boundary can occur, right? So things are happening on it. Work and heat is being done on the system, but there's no inlet. There's no additional mass coming in or exiting the system. Let's look at an isolated system. Nothing is happening, of course, right? It's a special type of closed system that does not interact in any way with its surrounding at all. There could be, right around here in the surroundings, there could be a blaze of fire, and it would not impact the system that we are observing at all. So now we're going to look at control volume in a transient operation. So you see you have mass flow going out, and you can see the flow going out. So we have all of those things that we talked about. We've got flow in and flow out, and so we've got a control volume transient operation, right? Okay, and then let's look at steady state control volume, okay? There you go. So we have no work being done on that. The boundary is staying the same. So you see the two differences right here. Sorry, you are actually having work done plenty of different ways, but nothing being done by the moving boundary work. Okay, so let's look at property, state, and process. So the state of a system is its condition as described by its properties. Property is a macroscopic characteristic of a system such as pressure, temperature, and volume, to which a numerical value can be assigned at a given time without knowledge of the previous behavioral system. So let's look and see what happens. So you see, so a gas or a liquid in the piston cylinder assembly is undergoing two separate processes. Processes 1 to 2. So let's go 1 to 2. That's expanding work, and then compression. Okay? And so then we are going to look at just some definitions that we're talking about an extensive property or an intensive property. And remember, a property that is called extensive is for which the sum of its value of its parts is divided. So you've got mass, volume, energy. Those are all examples of extensive properties. Okay? And then you've got mass, volume, and energy down there. And then you've got intensive, which is the value of an overall system is not the sum of its parts, right? And so you've got density, specific volume, pressure, temperature. It doesn't matter how big the system is. You can't add up all of its properties and get data for that if it's an intensive property, it's not going to work. But you can do that for extensive property. Okay, so let's look at density, right? So you've got lead versus air. It looks to be the same size, but the density is very different. Obviously, the lead is more dense, right? And so you've got density over here, mass over per unit volume, okay? And so then let's look at specific volume, right? So you've got lead, and then you've got air. Okay. And so then here we've got representative specific volume values for air and steam, two gases commonly used in thermodynamic applications are indicated below, and then we do use air and steam quite a lot. And those are the specific volumes for those. And again, remember that that's per unit volume. Okay? And remember, it's independent of the size or extent of a system, right? Specific volume is an intensive property. Okay, gases have specific volumes much greater than liquids or solids. Let's look at pressure. Okay, so this is a fluid at rest. And this F normal, that's force normal too. And then this is the area. Let's see what happens when we apply some pressure. Of course, it gets smaller, right? Okay, and this is taking the limit of A and then not A, right? Or A2, right? So for a gas or a liquid at rest, we consider pressure as the normal force exerted on a unit area, right? Pressure is the ratio of the compressive force, force normal, exerted by a gas or a liquid to an area. The pressure at a specific point is defined as the limit, right? Where A prime, so A with the little dot, is the smallest area for which a definite value of a ratio exists. Okay, then let's look at temperature. So, temperature is rooted in the notion of hotness or coldness of objects. When the temperature of an object changes, other properties change also. So you see that we went, let's see if I can restart it. So you see we had two copper blocks, A and B. B is colder than block A, and then when they're brought in contact and isolated from their surroundings, they will start to undergo a thermal interaction where they will eventually reach thermal equilibrium. And then again, temperature is a physical property that determines whether the blocks will be in thermal equilibrium. When the two blocks are in thermal equilibrium, their temperatures are equal. Remember, temperature is an intensive property, and again, we're going to measure that in Kelvin or Rankine. Okay, hopefully these were helpful.